Just start recording. Firoz, your screen is frozen. Okay, I think it got disconnected. Okay, so maybe in the interest of
Yeah,
time, maybe Ajil, if you can. Firoz, are you back?
yeah, I am back. I'm very sorry. I just had some network issues. I'm actually in India.
Yeah. Oh, okay.
So yeah, you can all hear me, right?
Yes, now we can hear loud and clear.
Okay, I'm so sorry. This is a great, this is an exciting topic today. We have generative AI, and we have one of the top experts with us, Ajil Jalal, Dr. Ajil Jalal. He graduated from the esteemed IIT Madras, completed his PhD from UT Austin, and has been doing a postdoc fellowship at UC Berkeley almost 3 years now. His research is focusing on generative models, information theory, and algorithm design and analysis. He is considered to be one of the top generative AI experts in the United States, so it is a privilege to have him join us today. He has been cited a lot, 3,000 times plus. He's an upcoming generative AI engineer, and today, I just wanted to say this too. His parents are also joining us today with me from Alua here. They are here with me, so it is also great to have them in this webinar as well. So I will
Absolutely.
let you start, Ajil.
Awesome. Yeah. Thank you for inviting me. I'm happy to be here. Uh, and also, I can't see the comments or whatever. So if you have any questions, just interrupt me. Um, I will try
Yeah.
to go slowly.
Yeah, we'll gather those questions, Adil, and also I know that the session is scheduled for an hour. Typically, what happens is based on the speaker's time availability and the audience. Sometimes we let it proceed further based on we don't have a official limitation that way, even though the session is scheduled for an hour.
I've
Yeah,
only
please go
made
ahead.
slides for like 45
Yeah,
minutes.
sure. Yeah,
Um, and also, I was hoping to do more than this, but then when I was making slides, I realized then I just wouldn't have time to cover all of it. So I've gone from 4 topics to 2. So I don't know. Maybe we can do a
that's all.
follow-up like a month
Yeah,
or two later and
sure.
just cover the rest of it.
Happy to do that. Yeah.
Yeah, and today's talk will mainly focus on images. So, and my expertise is in generative AI for images. I haven't done too much of language processing. And lately, I've also been doing some protein processing as well, which you can actually do using generative models. So, okay, let's start. Um, so, a question that people are asking almost 10 years ago is, I give you a million images and I want you to create new images. So, how would you do this? And this was kind of different from how people were viewing machine learning back then, because typically, I show you an image of a cat or a dog, and then I ask you to classify it as a cat or a dog. And instead, now what I'm telling you is I give you a million images of cats and dogs, and I would like you to create new realistic images, right? And now we know that there are many applications for these generative models, but back in the day, you didn't have any good models for them. So I'll just briefly talk about 2 very successful models that actually allow you to do this. Right. So um, all of these models are probabilistic models in some sense. So there's a little bit of a jump to go from images to probability distributions. And the way you should think about this is that I'm going to imagine that there's some true probability distribution of images, like say human faces. And then if I show you 1 million human faces, you have to think of it as random samples from some probability distribution. And then learning this distribution means that I've learned a probability distribution for these images in some sense. And then sampling means that I will draw new samples from this probability distribution I've learned. So for example, imagine I have 2-dimensional data. So there's one X coordinate and one Y coordinate. So you could think of it as like weight on the X axis and height on the Y axis. And then each dot over here would be a person who has certain height and weight. And then learning a probability distribution means that I have some sort of like heat map that captures how the height and weight are distributed for people. And now sampling from this would mean generate a new sample that respects this heat map. Wait, something happened to my screen. Sorry, can you hear me?
Yes, we can hear you. The screen is blank.
Yeah,
Yeah,
I'm not.
it's okay. We are able to see now. Oh, it's gone again.
Okay, sorry. I don't know what happened there. Right. So yeah. Right. So now the question that arises is why do you need neural networks for this sort of thing? Well, when you do probabilistic modeling in low dimensions, that's very easy. But then as you go to higher and higher dimensions, the space of samples that you need to cover just blows up. Meaning that if I consider a 1 million pixel image, then now this means that I'm learning this complicated function in a million dimensions. And this means that the number of samples I would need scales exponentially with the dimension. And then sampling from this distribution is also similarly difficult. So then we need models that can somehow work in this high dimensional space. And that's why we use neural networks. Right. So there are many different ways to sample probability distributions, but most of them boils down to this one key idea where you take some distribution that is simple, that you know how to sample from, and then you pass it through a good neural network, and then you hope that the output that you get is sufficiently complicated enough to capture the probability distribution that you're actually modeling. So one way to do this is there are these certain distributions that we know how to sample. So for example, if it's a uniform random variable or a Gaussian distribution, then we know how to sample this. And then what you can do is you take this simple distribution, you pass it through a neural network, and you get a new sample. And in this example, I'm going to take some, say, uniform distribution, which is these, say, one-dimensional latent variables that I'm going to call Z. I pass them through a neural network, and then what I'll get is something in a higher dimensional space. So in this case, if the red dots were training data that I got, once I have a good neural network, what I'm going to do is I don't know how to exactly sample in high dimensional space, but what I can do is sample in a lower dimensional space, sample from some simple distribution, and then make it more complicated by passing it through a neural network. I know that this is a very rough sketch, but this is the idea that you should have, that I don't know how to model things in very high dimensions, but what I do know is how I can sample in a very low simple dimension. And then I can pass that through a neural network to get a complicated higher dimensional distribution. Any questions so far? Is this okay? Hello?
I think we can, proceed.
Right. So now,
maybe Ajil, it'll help if you can explain a little bit on what do you mean by dimensions. I know you mentioned about low dimension
So one way to think about this is that you will very often hear people say that images are low dimensional. So what this means is if you take, for instance, a human face, then the pixels, for example, in the center of my forehead are very closely related to the pixels around it. And this means that it's not some arbitrary configuration of pixels. So there is some structure here that can be captured by lower dimensions, meaning that you don't arbitrarily change the pixels in the image, there is some structure that like that puts constraints on the pixels. And this is what we mean that by saying that lower dimensional. So another way to think about it is if I'm in a three-dimensional space and I can only walk on a line, then this would be an example of being constrained to a lower dimension, because although I'm stuck in 3 dimensions, I'm only able to walk on a line. And now if you go to higher dimensions, what this means is that, let's say in this case, I have variables that are only a single number, and then it gets passed through a neural network. And in this case, it becomes two numbers, the X and Y coordinates for each dot, right? And now there's nothing stopping you from scaling this up. So if you're generating images, it means that you can take like 10 numbers at the input, pass it through a neural network, and you'll get 1 million numbers at the output. Does that make sense?
Got it. So essentially you're saying, for example, the dot you mentioned on the forehead is typically the forehead will have certain constraints of color and look and the type of pixel that you will have there. And you expand it onto the next levels.
Yeah, exactly.
Okay. All right, thanks.
There is smoothness. If you didn't have any of these constraints, it would just look like, you remember when we had cable TV and your signal gets lost, you just get static noise. That is an example of an image that has no constraints or smoothness. Right? That's just like, it's just 1 million noisy pixels.
Okay,
but
thanks.
Natural images have more constraints, and this means that they're lower dimensional, meaning there are more constraints on them. Right. Okay. So essentially, nowadays, sampling means you take something that's easy to sample, you pass it through a complicated neural network, and you will get a complicated output. Right. So generative adversarial networks are it's a pretty neat idea, and they were invented in 2014. And I'll start with a motivating example. So, okay. So I want to generate fake currency. And let's say I have 1 million examples of currency notes. So like the serial numbers could be different, the watermarking could be different, and all of that. And I started 2 neural networks. And the key thing to note is that these neural networks know nothing. They're absolute idiots, right? And the first neural network is called the generator, which I will denote by the letter G. And this is trying to generate fake currency. And the second neural network is called the discriminator, denoted by D. And this is trying to detect if the currency note you produced is fake or real. And while these 2 neural networks don't know anything about currency when you first initialize them, they will know everything about each other going forward. Now, I show my generative neural network 1 million examples of cash, and I ask it to duplicate it and create new fake notes, right? And then I collect these fake notes and the real notes that I have, and I pass it to my discriminative neural network, and I ask it to classify whether an input image is a fake currency note or a real currency note. And since these neural networks know nothing at the beginning, they're going to produce something that does not at all look like a currency note. So for example, it may produce, the generative network may produce like square notes that are yellow, and then you pass it through the discriminative neural network. And this thing also knows nothing. So it's just randomly guessing whether a note is fake or real. But the thing is, since this discriminator is a neural network, I can train it using classical techniques to better identify what is a fake note and a real note. Because I, as the designer of this algorithm, know which are the fake notes and which are the real notes. And then I'll just tell the neural network, these are what you got wrong. And based on what it got wrong, it will update its own knowledge of the world. And then the thing is, once you update the discriminator, the generator also knows how the discriminator was modified. So then you can update the generator to create fake notes that can better fool the discriminator. And then you can keep going back and forth. So if I train the discriminator, after that, I will train the generator based on the discriminator. And then based on that generator, I can update the discriminator and I can go on and on. And essentially, the stopping condition for this uh, process is when the discriminator is just randomly guessing what's fake and what isn't. At that point, uh, the generator has successfully done its job and created fake nodes that the discriminator cannot classify. Um, and this is the motivation for generative adversarial networks. And it turns out using this, you can finally get a generator that produces very good fake images. Any questions about this? All right.
Hi, Ajit. This is Deepthi. Yeah, I have a question on this. So I'm understanding that so it needs to do the training and make the model to understand that what is right, what is wrong, like that. So do you know for this use case, how much time would be used to train this model?
Yeah.
What could be like average time will be taking to train this model?
Yeah, so that's a good question. And the biggest problem with these models is training time, and also they keep oscillating. So you would hope that they converge and reach a stopping condition, but turns out they'll um, they don't. It's actually very difficult to get them to converge. But in actual numbers, if you were to train a model for 1 million pixel images, then you could do it in under 6 or 7 hours using like modern GPUs. And there are very few theoretical results on how you can train these things well. So the the main problem here is that since I'm optimizing two models and they're trying to do the opposite of each other, optimizing them is actually very difficult and convergence is quite slow. And that's actually the biggest negative about these GANs. Did I answer your question?
Yeah. But like, is there any manually we need to say that this sometimes it's a prediction is wrong, right? So, is there any
Yeah.
manual intervention to say that, oh, this is wrong, this is right, something like that? So that takes time, right? So you, in case if that is needed.
Yeah, there is a lot of manual intervention involved. Essentially, uh, the biggest failure point is that if you have let's say, 1 million images, at some point the generator will just pick, say, 100 images and start producing those alone. Because if it figures out how to do a small set of images very well, it's difficult to tell whether that was fake or not. And yeah, you basically need a grad student to sit and look at whether these things are successfully trained or not. It's not there are no real metrics you can just look at. You actually need to visually inspect them as well.
Okay, thanks.
Yeah. There are
Ajil, just
pseudo metrics you can use that will tell you if it's obviously gone wrong or not. But at the end of the day, you need to visually inspect them. Yeah.
just a follow-up question on this one. This is Manoj. So, in machine learning, you keep training, and for every scenario, you have to train them, right? But in this case, for Gen AI, once it is trained, the neural network it's trained, then the model can generate that content by taking that input and then predicting the subsequent one, right? Like you give a start of something, it can complete that sentence kind of thing in a proper manner. So wouldn't it learn that way, like this fake currency one or any example that you gave? It can generate the content based on the input training that you gave, right? We don't have to train every possible combination scenario, unlike a standard machine learning, right?
That is true, and um, I disagree that it's different from standard machine learning, because even in standard
Okay.
machine learning, you can't really account for every possibility. You hope that your model's not memorizing stuff,
Yeah.
and you uh, uh, I mean, that's a very fundamental problem in both classical machine learning and generative AI, where you hope that Like for instance, a bad version of ChatGPT would be one where if you gave it an input, it always gives you the same output all over again, right? So you need diversity in some form. So just because you can create a valid sentence doesn't mean that it's a good model, right? Because like ChatGPT is good. It generates diverse outputs as you give it different inputs or the same input, but um yeah. Okay, I'm sorry, I'm struggling to answer your question.
No, that's fine. Understood. Like machine learning has that limitation, understood, but this one has more than
No,
that, right?
this would have it even worse because
Oh,
in this case you're not giving the generator much information, right? You're just giving it images and you're like reproduce. And even
okay.
ChatGPT, you just give it English sentences and you say reproduce it. So you need some mechanism to make sure that you're not just memorizing your data set. So this is
Okay.
actually harder than classical machine. Yes.
Okay. Thank you.
Okay. Now, in pictures, what this means is let's say I have a large training set of numbers. So these may be from like traffic signs or whatever. And now um, I feed real images to my discriminator, which is a neural network. And it has to tell whether an image is fake or real. And on the other side, I have this other neural network, which is taking some, say, pure noise, mapping it through another neural network, and which is the generator, and producing an image. And the discriminator has to decide whether it's a real image or a fake image. And you basically train these two neural networks alternatively based on one another. And I have sorry. So at the starting of training, this is what the generator's images are going to look like. And then if you run the training algorithm, it's going to slowly improve the images, very slowly improve the images. And these are different faces these are the different images produced at different training times. So it starts with absolutely nothing, starts producing slightly better images. And then as time progresses, the images get better. And these are generative models from 2016. So the faces are obviously not very good. But if you go to this link, it actually gives you a fully contained notebook. So if you go to this website and you click run in Google Colab, you can actually start training a GAN of your own. So it's actually very transparent and democratic. So you can get it to work with minimal effort. And the mathy version of this, I don't know if I should skip this or not, but I will very quickly run through this. So now I have a generator that's trying to create fake images and a discriminator that's trying to tell if an image is fake or real. The way you mathematically model this is that the discriminator produces a probability between 0 and 1 that it thinks that the image is real, which means that if it says 1, it thinks the image is absolutely real. And if it's 0, it thinks the image is absolutely fake. And anything in between is a spectrum on how real it thinks the image is. Now, since I want to maximize the probability that
image കേട്ടോണ്ടിരിക്കുന്നു ഓടി നോക്കണേ MBA മറ്റേ മെഷീൻ ലേണിംഗിന്റെ ഇതൊന്ന് കേട്ടോണ്ടിരിക്കുക അല്ല ഇന്ന് മറ്റേ ഓളങ്ങളുടെ 10
can you mute yourself, please? Okay, so mathematically, I want to maximize the probability that my discriminator is correct, which means that I look at the instances of real images which were correct, and I look at the instances of fake images fed to my discriminator, and then I'll see whether the discriminator got them correct or not. So for the real images, I want my discriminator to say 1, and for the fake images, I would like it to say 0. And you can forget about the logs, but it's just to make optimization easier. And then what I want the discriminator to do is maximize this summation. So I sum over all the real images I have and the fake images I've generated, and I would like the classifier to label them correctly. Now, these fake images were created by a generator, which means that I sampled some noise Zi, I passed it through my generative neural network, and I get this image G of Zi. So if I replace that in the first equation, what I'll get is summation log of D over the real images plus the summation of log of 1 minus D over the fake images. And now the discriminator wants to maximize the probability of detecting fake versus reals, but the generator wants to minimize the probability that it can get detected. So while I had a max over D over here, I'm going to have a min over the discriminator, over the generator. So this is what you call a min-max game, because I have one agent that's trying to minimize a certain utility function, and I have another agent that's trying to maximize the same utility function. And these two are in direct conflict with one another. And once you optimize this, once you reach some equilibrium where neither of them change, you hope that the generator is actually good. This isn't too important. I just wanted to give you a feel of what the optimization function looks like. And this function can be optimized using classical techniques. Convergence is not guaranteed, but in practice, there have been algorithms that can get this optimization to converge. All right. So in 2014, this is when they were first created. This is what the images look like. So on the highlighted ones are images from the training set, and the other columns are fake images generated by the generative neural network. And you can see that, they're plausible images, but they're not very good, because obviously this is the first instance of GANs. And then 2 years later, there was DC GAN, which was able to generate RGB images of human faces, and this was considered a significant breakthrough. And then in 2017, there was work out of NVIDIA, and this is called a PG GAN, which is progressive growth of GANs. And you can see that these images are actually very good, and they are almost a million pixels, and the model is actually very capable even back in 2017. And then in 2019, there was Big GAN by Brock et al. And this was superb. It was very difficult to beat this model, and I think it took almost 3 years to beat it. And the main differences between these models is the model architecture and the optimization algorithms involved. And the core problem that you needed to address is exactly what Deepti asked, as to like how do you optimize this and guarantee convergence? And turns out with a few years of work, we were able to get images that were we were able to get generators that were only able to produce images, but that were only able to produce numbers. And now in 2019, you can get like very, very authentic real world images. And then 2021, there was a paper out of OpenAI by Dhariwal and Nicole that showed that diffusion models are able to beat GANs. And this is an entirely different family of models, which I'll talk about next. But I will stop over here to ask if there are any questions. I wasn't sure if I ran through that too quickly or not.
Looks like we can proceed. I don't see a question on chat also, so yeah.
Okay. Right. So diffusion models, these appeared around 2021, and they are very popular now. So for instance, if you remember DALL-E or Imagine, these were models where it was finally possible to give it prompts that were very long. So for example, if I say two dogs that are playing with each other, that is not something a generative model could have done back in 2021. And with the invention of diffusion models, that actually became a reality. And now most of you should be familiar with ChatGPT, and there's a lot of material on ChatGPT that you can read, but you can actually generate language as well using these diffusion models. I won't have time to go into how you can model language using diffusion models, but the same techniques I describe over here that are used for training images, you can directly translate them to natural language. Right. So the main problem with GANs is that I had this min-max optimization where I had a generative neural network that's trying to produce fake images, and I have a discriminative neural network that's trying to tell whether an image is real or not. And this sort of min-max optimization is very difficult. There are many negative results out there which show that it's not actually possible to do it in a reasonable amount of time. And what we observe in practice is that the discriminator typically wins against the generator. And this makes intuitive sense as well, because the generator has a very difficult job. It needs to take pure noise and transform it into meaningful images. Whereas the discriminator, all it has to do is tell if an image is fake or not. And there's no principled way to combat this. The only thing you can do is make more updates on the generator compared to the discriminator. So for example, for every 10 updates you make to the generator, you make only one update to the discriminator. And the problem here is that you're asking too much from a generative model where you're asking it to create an image, and then its adversary, all it has to do is label an image as fake or real. So one way to combat this is to break your problem into smaller chunks. So a GAN would have gone from pure noise to an image in a single step. Instead, what diffusion models do is break this down into smaller digestible portions. So instead of going from pure noise to a clean image, what it's going to do is take noise, make it less noisy, make it less noisy, make it less noisy, make it less noisy, and you keep going until you have an image that you're satisfied with. And don't parse the math over here. I'll explain that in a bit. But the key idea here is that what we basically do with diffusion models is create a process where I can go from clean images to noise, which is called the forward direction, where this clean image gets slightly noisy, more noisy, more noisy, more noisy, and so on, until it's just pure noise. And then the reverse of this is the generative process, where I go from noise to less noise, to less noise, and to less noise, and to clean image. So I will describe this in more detail, but the reason diffusion models have an easier time is that I've gone from one big problem into smaller digestible problems. So I don't have to solve one big problem. I break it down into 1,000 smaller problems. So the way you create the training data here is you take clean images without any noise, and then you just add noise of varying amounts to these images, and you create a data set. So this is called forward diffusion because I'm taking images in my training set and I'm going to add certain levels of noise to these images, and I will create noisy images. So what this means is I pick one image, say of this dog. I'll generate random noise. This is very easy to do. There's this traditional computer like Python functions that will generate this noise for you. And then I'll pick how much energy I want to have with this noise. So this is a whole spectrum of noise that I could have. I could have very little noise, a moderate amount of noise, or a lot of noise. And let's say in this example, I pick a moderate amount of noise. I will now add this to the clean image, and I will get a moderately noisy image. So if I were to pick a small amount of noise, then the image over here would have more dog than noise. In this case, it's like 50-50 between dog and noise. And if I were to pick the last one, it would just be pure noise. And since noise is easy to generate, you can just arbitrarily choose how much of noise you're going to add. Now, the data set over here is it's actually very easy to generate because all I need to do is take a data set of clean images, add noise to it, And then these noisy images I'm going to call them the input. And the noise that I added to this noisy image will be the label. And then the neural network will learn to predict the noise given this noisy image.
More or less like a reverse engineering kind of thing, right?
Yeah, so this is how to go from images to noise. I'll describe noise to images later, but yeah, this is what they call the forward process, where you're creating noise from images, and then you will reverse engineer on the opposite side. But the key point here is, as you pointed out earlier, in classical machine learning, you have an input and you'll have a label, and that was missing in GANs. All you had were images, right? But in this case, I've gone from generative AI to some midpoint between generative AI and classical machine learning, because instead of just trying to model clean images, what I'm trying to do is look at the noisy image and try to predict what is the noise in that image. So this is much more closer to classical machine learning, where I have an input and a label. But in this case, both the input and the label are of the same dimensions. So the input is a noisy image and the label is noise in that image. Is that okay?
Yep.
All right. So now the neural network that I'm going to use will accept a noisy image from the data set. And then I'll also tell it how much noise is added. So this is just a single number, which tells me what is the energy in the noise that I added. And both of these go as input to a neural network, which is trying to predict the noise. And then I will get some predicted noise as output from the neural network. And then I'll compare how close this predicted noise is to the actual noise that I added to the image. And note that since I added the noise, I know what it is, right? And I would like the neural network to match the actual noise as closely as possible. And then using classical machine learning techniques, I can look at how different the predicted noise is to the actual noise, and I can update the neural network accordingly. So there's feedback over here because I've taken a noisy image. I haven't shown the neural network the label. I also know how much noise went into the image, and there will be some predicted noise. I'll compare it to the actual noise that I've kept hidden from the neural network, and I will update the parameters accordingly. Okay, so this tells you how you can remove noise from a noisy image, but how do you actually create new images? Well, since I have this neural network that is accepting a noisy image, and as well as what's the level of noise that was added to it, once I get this predicted noise, all I need to do is subtract it from the noisy image. So noisy image goes in, predicted noise comes out. And then if I take the noisy image and subtract out the predicted noise, I will get a less noisy image. Sensible, right? And now if I do this iteratively, I can consistently keep improving this image. And I can go from pure noise to an image that has like 25% cat and 75% noise, to an image that has 50% cat and 50% noise, and finally an image that's purely a cat. So this one step where I was taking in a noisy image, feeding it to a noise predictor, getting predicted noise, and subtracting that from the noisy image, there's nothing stopping me from running this process over and over again. And it's the same noise predictor. All that changes is the noisy image that goes in as input and the noise level. Does this make sense?
Yeah. So when you first put that, the noise image, right? And when you arrive at the noise, like what kind of noise you want to inject onto to make the subtraction. So how do you know first that, okay, it's a cat or it's a dog? And based on that, only you put the noise, right?
No, you don't know that. So you can, so the model I described, you don't know if it's a cat or a dog. You only know that that's like I tell the model how much noise is there, and I show it the noise. And now if my data set is only cats and dogs, then 50% of the noise, or like if I sampled, let's say 100 initializations of noise, 50% of them would be cats and 50% of them would be dogs. In this way, in this case, there's no way to control for a cat or a dog. You will just get a random sample of a cat or a dog.
So it all
But
depends on how big the data set or the kind of diversification of
yeah,
your thing is, basically.
yeah, that whatever diversity you had in your training data set, that's what you will get at the output
Okay,
as well.
okay, gotcha. Thanks.
But you can create more complicated models. I didn't want to go into it, but you can create models that accept a label as well. So if I tell it I want a cat, it will give you a cat. If you say you want a dog, it'll give you a dog. And as long as you had enough examples of cats and dogs in your training data set, you'll be okay.
Got it. Okay, thank you.
But this model itself, there's no way to control for a cat or a dog.
And this can be used in wide variety. Like, for example, in the military and all, we can use this model, right?
Yeah, yes, you can. The military is actually quite excited about this because they work with very noisy images. And
Yeah.
since I'm now using a denoiser that is capable of producing images, it's like shooting two birds with
Got
one
it.
stone.
Okay.
Yeah.
Thanks.
Any other questions? Okay. This is going much quicker than I thought it would. So okay, so when I first saw this, it doesn't make too much sense, right? Like, why is all I've done here is I haven't really created an image generation model. All I've trained is this noise predictor, which can take in a noisy image and give me noise that I would subtract out from the image. So it's not quite clear why this works. And mathematically, it has a very interesting interpretation. So there's something called Tweedy's formula, which says that let's say you have this noisy variable x tilde, and this x tilde is generated by taking a clean image x and adding some Gaussian noise to it, where the Gaussian noise is such that it's zero mean and has some variance. And now sorry, was there a question? Okay. So Tweedy's formula says that if I have a clean image and I add some Gaussian noise to it and I get a noisy image, then the conditional expectation of the clean image conditioned on the noisy image is the noisy image plus the variance in the noise times this gradient of the log of the probability density of x tilde. So this equation is a little difficult to parse, but essentially what this tells you is that there is, okay, so I'm speaking to engineers. So if you density associated with the clean image as, say, electric potential, then this gradient log of the density would be something like the electric field. So this equation actually tells you that you can relate the conditional expectation of a noisy random variable using the noisy random variable itself plus the field associated with the noisy random variable. And if you rearrange this equation, you should know that the conditional expectation of the clean image condition on the noisy image is the best estimate for the clean image. And now if I do this conditional expectation minus x tilde, that is actually the best estimate for the noise. So what this tells you is that the optimal noise predictor you have is actually beta square, which is the variance, times the field associated with your probability distribution. And in literature, this thing is called the score of the distribution. And the key thing to note here is that once you have this, it actually it makes sense as to why you're able to generate images. So if you think of again the electric potential interpretation, the probability density associated with my image is, it takes in an image and it gives you a single number as to how likely this image is, and the gradient of the log of this density is the electric field. So while the density is just a number, this gradient of its log is a direction that you should move in. And now, going back to the electric potential interpretation, this field tells you if I have an image that is, say, slightly noisy, so in this case, let's say I have this noisy image of a dog over here. Uh, so let's say I'm at this point on the PDF, yeah? So this density tells me how likely an image of a dog is. And let's say I'm at this starting point over here where I have a noisy image of a dog, then the 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 denoiser is going to tell me how I should change this image of a dog such that it's more likely under my probability distribution. And that is exactly the gradient of the log of the density. So I will pass this noisy image into my noise predictor. It will tell me how I should modify it. And once I modify that, I will get a more likely image. And then running this model over and over again just means that I'm going to go from this less likely point to a more likely point to a more likely point and so on. So the final image I get will be a very likely image. I don't know if this helps or if it made you more confused, but if you have any questions, I'm happy to address that as well. Okay. So it's been 50 minutes. So if you have a Q&A session, I'm happy to do that. But I also have backup slides in case you would like to go through that as well.
So what are the kind of real-time use of these things, like in the day-to-day kind of practical uses of this?
Excellent question. Sorry. Okay. So if you ever go to do an MRI scan, then what happens there is that you will okay, so the MRI machine is very non-invasive, meaning that it doesn't get images of your brain. What it does get is, let's say X star denotes your brain. It will record some auxiliary measurements of the brain. So what that looks like is so the MRI machine is not going to give you this image of a brain. It's going to give you some just like black and white dots that look like this. And turns out there's an interesting relationship between these black and white dots and the brain, and it's actually described by the Fourier transform. So I'm not going to explain how it does it, but the MRI machine will essentially do a Fourier transform of your brain, and it will give you the corresponding Fourier coefficients associated with your brain. And getting a high resolution brain scan means that I recorded a certain number of Fourier coefficients. So if I record 1,000,000 Fourier coefficients, I will get 1,000,000 pixel brain scan. If I record only 1,000 Fourier coefficients, I will get 1,000 pixel brain scan. And now the number of Fourier coefficients you record determines how good the brain scan is. Now the problem here is that if you want to record more and more Fourier coefficients, then it increases the scan time, it increases the cost, and it also means that you have to sit in the machine for a long time. So so let's say that this image on the bottom left is the gold standard. So this is these are the number of pixels that a radiologist would like to see. And now let's say I'm being very cheap with using the machine, and instead of recording all the Fourier coefficients I need for this brain scan, I only record every 1 out of 12 Fourier coefficients. So I'm not being clever with it. I'm just going to lazily record only a 12th of what I was supposed to record. And if you pass that through traditional machine learning models or signal processing models, you'll get these noisy, shaky brain scans. That's because I just didn't collect enough data from the MRI machine. Whereas if you train a generative model that knows what a brain looks like, all you need to do is tell it, I recorded some number of Fourier coefficients, and my generative model knows what a brain scan looks like. So conditioned on these Fourier coefficients I recorded, can you tell me what the actual brain looks like? And turns out if you use a generative model, you get this image on the bottom right. And this is my work uh, where essentially we showed that if you have if you only have a certain amount of MRI data, and also if the patient is moving and so on and so forth, you can use generative models to create very good looking images. So the applications for image generative models are huge. So you can use them in medicine, you can use them for military applications. Most recently, it's just been used by people playing around with DALL-E and Imagine, but there are
Got it.
actual financial
So,
applications here.
so on this note, on this MRI scan note,
Yeah.
maybe it's a really dumb question. Okay, so for example, if there is a patient who has a special new growth on his brain or something, okay, I'm just calling it out. I'm not very into the medical field. So you have all those images of a real brain kind of thing, okay, the actual thing, but this person has a special condition, have a specific growth which is not found in many other things, many other people. So when you create an image, you will go to that whatever images you have, which is like the ideal brain. It will not capture the special growth that this person has, right? So how will then the diagnosis will come into picture then?
Right. That's an excellent question. And yeah, so the key thing to note here is that you're not just, I'm not asking the model to hallucinate what a brain looks like. I am using this in conjunction with an MRI machine. So the machine, when I do this, it will be at a scale where it's actually safe to do it, meaning that there is
Ah,
still
got it. Okay.
information about that tumor from what the MRI machine recorded.
Okay. Okay. And then you develop the cleaner one. Got it.
Yeah. Yeah.
Okay. Okay.
It's
Thank
not just, you don't want to go too aggressive with this. So currently, radiologists will only go to a subsampling of, say, 4, because
you.
beyond that is actually very risky.
Got it.
This is more of a prototypical experiment where, like, listen, you can go to 12 in principle, but yeah, it's probably not safe to do it. So
Yes.
this experiment would not be done in an actual MRI lab.
Got
But
it.
But where these things can be useful is, let's say, if you put a child into an MRI machine, then a big problem that radiologists have is that children get fidgety because they're claustrophobic in an MRI machine.
Mhm.
And if you move during an MRI scan, it leads to this motion blur.
I see.
And you can use generative models to remove this motion blur.
Okay. Okay.
So you have all of these nice applications.
Got it. Thank you. Thank you very much.
There are a few questions on the chat. One of them is saying, from a young crowd, from the kids, what's the difference between Gen AI and machine learning? That is one of the question. Then another question. Aromal, your question is very big. Probably you can ask that directly. And I saw there was a question from Justin. I don't see that anymore now. Yeah, so first one was the difference between Gen AI and machine learning. The question is from some of the younger participants of the school.
Right. So typically, okay, so Gen AI is still a part of machine learning, just to be very clear. But yeah, the main difference is now people say generative AI and say, like, if they will tell you, if they say machine learning, it typically means like it would be a classification task. So for example, is this an image of a cat, or is this an image of a dog, or is this an image of a human? So those are questions that are slightly easier to address because you're going from very high dimensional data, which is, let's say, I'm taking 1 million pixels, passing it through a neural network, and all I wanted to tell me is cat, dog, or human, right? That problem is much easier than actually generating an image of a cat or a dog. So generative AI is like taking classical machine learning and flipping the dimensions. So instead of going from an image to a label for the image, generative AI goes from the label for the image to an actual image. Does that make sense?
Yeah, Shima, I think if you're there, so that was a response. And maybe considering the time, I know that we are on time, but we can still proceed. The next question is slightly big. Ajil, I don't know whether you want to open the question and read just to make sure I don't miss anything on that, or Aromal, you can ask the question directly.
Sir, I have been experimenting on stable diffusion from a long time.
Okay.
Yeah, every time when I try to create a human image, I often encounter deformed fingers and disproportionate body.
Okay.
How to fix that?
Exactly how complicated are the prompts that you're using? Like, is
Prompts are
it
simple.
okay? Give
Prompts
me an
are
example.
often simple, but I have given a lot of negative prompts as well,
Okay.
so as to prevent those deformities. But
Right.
still, those deformities coming again and again.
I mean, if the stable diffusion model is like that, then there's not much that you can do. There have been uh, uh, okay, I don't know if this is a acceptable kosher answer or not, but I know a professor who trained diffusion models on like pornographic images because, well, they're human bodies and there's a lot of it around. So if you train it on a data set like that, it actually gets the human body fairly correctly. And, it doesn't have to be porn strictly. It can make like regular humans, but to get the proportions of a human body right, it's actually difficult because typically models see very, they see what a human looks like. It's not so much about like body parts and consistency between the body parts, right? Like joints and all of that can be in arbitrary directions. But there does exist a data set out there where you can train on human bodies that are representative. So that's not a great answer, but I do know that Kangukli, yeah. There are ways to address it. You should be able to find better generative models that have been trained explicitly for that. And but there are these websites that will tell you if you have a particular data set in mind, then you can use what's called LoRa, where if you give it examples of the sort of data that you want to generate and fine tune on, then you give it this small data set and you can fine tune on it. So you should consider maybe using this thing. It's called LoRa.
Thank you, sir.
Yeah. Okay.
Justin, do you have a question?
No, I don't. He basically answered my question earlier, so it's fine.
Okay. So we still have the open time now. Anybody has more questions?
One question here, Naveen here. what about mixing these two models that you discussed, right? One is the GAN and the other one is a diffusion model. So within GAN, you said it can be broken into small pieces, and or the reverse actually in diffusion model. So you select small samples or pieces of it, and then can you apply GAN on top of it?
Yeah, actually you can. So if you so stable diffusion actually uses adversarial training and diffusion models, and the reason that GANs are good. Okay, so is your question like, should you use a GAN and then a diffusion model in your pipeline, or is it like within the GAN you should use like diffusion model techniques?
Either ways, I mean, a possibility of using the best of two worlds, right? I'm just asking that.
Right. So stable diffusion actually does that. So So stable diffusion actually uses three of them. So there is okay. So okay, to draw parallel to existing work. So we have fancy encoder and decoders for compression techniques like MP3, where you feed it audio signal, you'll get an encoding for it, and then there'll be a decoder that goes from that encoding to an image, to a waveform, right? And now stable diffusion has such an encoder and decoder. So E is an encoder, D is a decoder, and the diffusion for this thing happens in the encoding space. So it's not, if I take this million pixel image, stable diffusion doesn't run diffusion on the million pixels itself. It compresses it to like 1,000 dimensional latent space, and it does diffusion in the latent space. And this encoder and decoder are trained adversarially. So the there will be another discriminator network on top of these that train a good encoder and decoder.
I see. Okay.
They actually combine like three models, which are autoencoders, GANs, and diffusion models. So you can get a best of both worlds. And in audio processing, what they will do is, if you're familiar with like say like the short-time Fourier transform, which is used a lot in audio processing. Instead of using just the short-time Fourier transform, they will use a variational autoencoder to take you to this representation of a waveform. Then they will run diffusion in the representation space of the waveform. And then to generate the final waveform, they will go from the representation generated by the diffusion model, pass that through a GAN, and then get the waveform. So modern signal processing actually uses typically all three models. I didn't get to talk about variational autoencoders today, but if you want to do another session a month or two from now, I'm happy to do that as well.
Absolutely. Maybe one more follow-up question. It's not a follow-up question. It's a completely different level question. So if you can at least give, because a lot of attendees are here who would be looking at the new career options or new things that are happening in generative AI or even AI in general. So so many apps are coming, so many different models are there, Microsoft, Google, everything, right? They have their own models. How do you denoise it? And in the sense that, say, if someone wants to pursue a career path in AI, what are the options someone should look at from a very, very high level point of view? I know it's a very loaded question, but still some kind of direction in terms of,
It's a good question. Good question.
Yeah.
Okay, so typically I would say that if you're just getting started with generative AI, then images are probably the data set you should work with first, because it's very, you can look at it, you can tell whether your models are performing well or not. And also there are all of these, almost free notebooks out there that will, like, for example, PyTorch, the tutorials itself have a bunch of things that you can run on Google Colab, which is free. So you don't have to pay for these GPUs. And if you're going to do more expensive work, there's this website called vast.ai where you can get GPUs for like 10 cents an hour. So, and these are very, very good ones. So if you're typically, my answer would be you should first try joining a lab. And if I assume most people here are in India, most students here are in India. So if you, the free option to be messing around with these models is Google Colab. And you actually get fairly decent models here and, sorry, fairly decent GPUs here. And you should explore Hugging Face models for the latest ones as well. And yeah, I would actually say that if you're trying to learn about what are not exactly the latest things in Gen AI, but the first version of the latest things in Gen AI. So for example, ChatGPT uses, or at some point used, a BERT architecture. And it's not you're not you won't be able to access ChatGPT, like the internal architecture of ChatGPT right now, but you will be able to play around with a more elementary version of the same architecture that it uses. And you should probably try experimenting with that. Use the free online GPUs that Google Colab provides you. And yeah, trying to find projects with professors is probably the best path, because I think there's a huge barrier to entry here, because you need to know someone who knows someone who can get you a job, or so on and so forth. So working with professors, getting your foot in the door, establishing that relationship is probably the most important thing. And even like when contacting them, you should say that you've played around with these models, show some initiative. And yeah, I think Hugging Face is a very good place to start. Just look at the latest things that's going on there, play around with the models. Some of them will be free to use on Google Colab as well. So I don't know if that's a decent answer to your question or not.
No, it really helps.
Yeah. And I think, Param, you have your hand up.
Yeah. Hey, thank you, Ajit. And it's sort of linked to what you just said, projects, Ajit. So for the students, I know they're in their final semester or their pre seventh semester. So how do they go about doing a project on this? What are sort of the practical steps of doing a project using these technologies? And if you can just share.
Okay. So it broke in between. So could you repeat your question?
I'm saying, students who are in their final year, they have to do projects, and if they need projects using these new technology, how do they go about doing it? What are the practical steps? What are sort of examples of how they can, you said putting their foot on the door, so that when they have campus interviews, they can say, hey, we did these projects on this. So what are some examples, and how do they go about doing those projects?
Yeah, okay, that's a good question. So okay, so if this is your first project in Gen AI, then maybe you should stay away from training a model from scratch. So, for example, there was a question earlier where someone said that when generating human bodies, they was just giving like weird stuff. You, instead of trying to train stable diffusion from scratch, that is prohibitively expensive. Like it's just not feasible. You can try to take an existing model, fine tune it on some data set that you think is interesting. So maybe you can you can like find a representative set of examples that fix the human body problem associated with stable diffusion. And yeah, I would say fine-tuning a model on an interesting application is probably the best way to go. And recently, things like DeepSeek have also been enormously successful. And the difference between DeepSeek and traditional Gen AI is that DeepSeek uses reinforcement learning to train these generative AI models, and it doesn't. It's almost like now there's a battle between whether using RL is the right thing or whether fine-tuning using small, good quality data sets is the right thing to do. So yeah, I would say either fine-tune an existing reasoning model on an interesting application, or fine-tune an existing diffusion model on an interesting application. A lot of people are now using diffusion models for code generation. So in my talk, the diffusion models are only for images, but you can actually do it for language and code. And this has financial implications as well, right? Because if you create a good code generation engine, it's a $1 billion industry. So yeah, I guess find a niche area, but not find an area that's not completely crowded, but that's also not too nichey. Fine-tune an existing large model to some interesting application that you can find. I would say that's the best approach if I were to do it from scratch again.
Thank you, Ajit. Very helpful.
Hey, Dr. Jalal, this is Anil. I have a question slightly different. Nice talk, very much focusing on the technical aspects of ChatGPT and generative AI. So my question is about on a different aspect. So you kind of like started touching upon the cost of using or doing the activities in the generative AI, which is, yes, you mentioned one part, which is the use of GPUs that is getting more and more expensive these days, both from the cost perspective and the availability perspective.
Yeah.
The other aspect of the cost of running those data center and the use of electricity. So, these days data centers I'm actually in the data center business. I run an HPC data centers globally.
Yes.
So the use of electricity becomes kind of a complicated topic. Some of the data centers are using more electricity than some cities, combined. How, and that both, a resource availability point from a, equity point of view are raising some concerns. How do you see these kind of topics in your community, in your practitioners community? Any thoughts on that?
No, I don't see it positively, because I think it's a very real case of rich getting richer, and even universities can't compete with corporations at this point, right? So yeah, universities are falling behind, and it's very, very, very expensive, and even like professors are struggling a little bit with it. So I don't have a good answer to that. I think the lack of equity is just going to get worse. Yeah, I don't see an easy solution to this.
I guess that's one aspect of that. The other aspect of that, it is even realistic to expect. You mentioned the to get an accurate image of MRI, the MRI image, you got to spend a lot more in order to get the accurate image. So is it viable to do the kind of things that we are trying to do at the scale and accuracy is required to be useful, right?
Yeah, definitely. If you're talking about MRI, I think it actually makes MRI much more equitable, because it makes scans cheaper, and you could work with, for example, an MRI machine needs a certain magnetic field within it. So in the US, they do 3 Tesla scans. in India they do 1.5 Tesla. And now if you were able to do 0.75 Tesla, that would be a huge breakthrough. And I think generative models would actually be very useful there. And the key point there is you don't need to keep training generative models, right? You train one good one and that's all you need. So it's that the cost of the generative model is actually very small compared to the actual cost of the MRI machine. So in that case, I think generative models are actually much more like
that's
once
a
you
good
get a good one,
example.
it's equalizing.
That's a good example because the sample size or the data size is smaller, but when it comes to like automatic driving and whatnot, that becomes far more data intensive.
Yeah. Automatic driving. Yeah. Yeah, those applications I can only see like rich getting richer. Because I don't think anyone ever thought about like automatic cars for like, I don't know, lower classes, right? It's not it's a very upper middle class to upper class thing. So I don't know if that's answering your question or not.
No, I understand. I just wanted to get your thoughts and how you guys think about this topic in your community of practitioners. Yes,
So
get
if
that.
you were explicitly asking about autonomous driving,
No, not really autonomous driving per se, but it's about the cost of progress in generative AI, the electricity usage, and the equity topics. Right?
yeah, some people do it, but I guess the people who actually build the models are like the important ones. Yeah, there's not really a okay. My hot take on it is that we've so like GPUs, for instance, like like none of these are created for machine learning applications, right? Like it's basically meant for gaming, and then they realize that you can actually use it for machine learning, and so it's not the hardware is not really optimized for uh, like machine learning per se. I feel like right now when they do it, it's okay. Yeah, they have some processing units, but a lot of it seems to be like they have a decent machine for gaming, and then you just put more transistors in and make it
No,
start.
well, that's actually a thing in the past. I mean, yes, that was true. It started with the gaming cards, but these days the GPUs are specifically designed for AI with all the tensor cores in it. I mean, we are struggling to get
That's fair.
the transistors for general processing.
Okay, that's fair. That's fair. But yeah, I don't know if they like fundamentally did it or even when they do it, I don't know how much of it is true. Like when they say design for AI, like because okay, TPUs for instance, whatever happened to them? I remember Google was saying that like these are things that are designed from a machine learning perspective, but like just never heard of them again. But
Yeah, well, OpenAI just signed up for Google TPUs. So
oh, I see. Okay. Okay, so it's not just a few processing cores within the
no,
GPU. It's a TPU itself.
yeah, it's a
Okay.
real thing. Yeah.
Okay, that's nice now. Nice.
Oh, thanks.
Okay.
Diti, your hand is up.
Oh, okay. Thanks, Manoj. Yeah, thanks, Ajit. So my question is related to, that we have earlier days, it was more focused on the regular ML models like the regression and classifications type, and also these days it's more trending on the LLMs. As you mentioned, there are so many in the hugging phase and all. So do you see, is there any trend that the relevance of the machine, I mean the ML models, like the classifications regression is going away and to take over by the LLMs? So do you see that? So just want to know that like where exactly you need to put more focus on.
No, I don't think it's going away. No, regression and classification, no way, because there's just so much economic impact created by them. And really now the question is like, okay, so for ChatGPT, we found a way to bridge the gap between research and monetization, right? So now like LLM research will happily continue for many, many decades because there's clear financial incentive to create better LLMs. But diffusion models, for instance, it's the gap between research and monetization is very high right now. So there are labs or startups that are trying to monetize based on diffusion models, but it's actually quite tricky. So even if you think about OpenAI's diffusion models like DALL-E, it didn't make any money until they said, okay, we're just gonna, if you subscribe for ChatGPT Plus, you get DALL-E with it. So it's more like we'll give you this for free if you sign up for a ChatGPT subscription, right? So I think I don't think regression and classification is going anywhere. Like those things actually make money. It's how do you get Gen AI to make money for you?
Okay. Thank you.
Not going anywhere.
I know that we are almost 30 minutes past, but it was because of the interest of everyone. And I just wanted to check any more questions, anyone? Okay. If not, Doc, I know that we went over and beyond, and Ajil, thank you for your patience, answering all the questions, taking time to staying back, and all of them.
It's better when an audience engages. It's not disheartening.
And based on the interest, I'm assuming that we will reach out to you again for another session sometime shortly. Maybe we'll coordinate that with Feroz to get that. Really appreciate your time and giving this overview and the detail, not just overview, the details and answering patiently all of those. Thank you very much. And thank you all. And have a good weekend. Appreciate that.
That's great. Thank you for attending.
Thank you.